Hello everyone, here's another video on uniform circular motion. This time we are looking at banked corners with friction. So last time you'll recall that we looked at banked corners without friction, which would probably be represented by this ball going around on a banked corner. If we assume there's no friction between the ball and the surface, if we get it at the perfect speed, it's going to keep going around and around at this distance away from the center, this radius. If it wasn't moving, of course, it would roll down. And if it was going faster than this perfect speed, it would slide up the ramp and shoot off. So there's this last time on the video we talked about the perfect speed with which an object can maintain circular motion on a banked corner without friction. Today we're going to talk about what happens when we do have friction. So let's get rid of this and bring in something like this. So this is a real photo taken of an extreme banked corner. This is possible because of the speeds that the cars are driving. And of course, what we're interested in here is the contact between the tires and the tarmac. So here's my cross-sectional view of the banked corner, and like any good physics student, I'm going to go ahead and start looking at the forces, drawing a free body diagram, just like we did in the previous non-friction example, although I might as well go ahead and just state from the beginning that in this case the mu does not equal 0, so we have friction. Let's go ahead and put the FG on. Let's go ahead and include this angle, theta. Let's keep going and put on the force normal acting on the car as a result of that gravity and the fact that it's on a slanted slope. That's the force normal perpendicular to the surface that it's acting on. And of course, that will be comprised of a component and another component here. And that's a right angle triangle, and we'll call this Fn sine theta, since this angle here is equal to that black angle labeled there. And this is Fn cosine theta. Okay, so the question is, whilst we were traveling at the perfect speed, so that when mu was equal to 0, there was really just a balanced condition so that there was a speed that enabled it to maintain the constant radius. So the speed that allowed the radius to be constant. Okay, now what we need to think about is if that speed goes higher, so whatever this speed is, if this goes bigger, so if we go faster, what's going to happen? And then also what's going to happen if this goes slower? And this we can do intuitively. So let's think about it. If the current situation with the car and the free body diagram that I've just drawn, this is assuming that there's no friction. So far we've not put any friction on. So if we think about the contact between the tires and the road, if there's no friction and it starts to go faster, hopefully you can intuit that the car is going to start to experience, or it's going to start having a tendency to want to move this way. There's going to be some speed that makes it move up the ramp. And if you go too fast, of course, you're going to fly off the ramp and disappear off the track. Okay? Conversely, if you go too slow, or if you're going slower than this speed that is allowed for the constant radius with mu being equal to 0, in this case, it's going to slow down and the car is going to have a tendency to move down the ramp. So in both these situations, of course, friction is going to be opposing that motion. So if we just focus on for a second, let's imagine that the speed is greater and the car is going to have a tendency to move up the ramp, then of course friction is going to be acting against that motion. So that would be the force of friction. And vice versa, if the motion of the car was to slide down the ramp, so if we put the motion to be going this way, if the speed was slower, the car would start to fall down the ramp, then the frictional forces would be going up the ramp. Okay, so this is a very important physics concept to get nailed down right away, because that's going to affect how we do our FNet expressions. So let's go ahead and do it for this situation, where we have the speed of the car being lower than what it would have been at mu equals 0 to maintain that R constant. So it's the slower speed. That means the car is going to have a tendency to drop down the ramp or down the curved bank, but because of friction, it is not falling down the ramp. So these two forces are going to be equal to each other. And what we'll do now is just add on some vector components to the force of friction, and then we'll go ahead and do our XY analysis. So hopefully you can see, of course, the force of friction is going to have a X component to it, and this angle in here, this yellow angle, is also going to be equal to the red angle. That's obvious, hopefully you can see that, because this red triangle has simply been rotated 90 degrees. In addition, you can think of the parallel lines. Maybe I can just draw them in here. If this is a parallel line and this is a parallel line, then really we've just got this intersecting line here, and that would be the origins of these angles, the intersecting parallel line theory. So we are going to label these components, because of course there's one going up, and so this would be the force of friction cosine theta, and the one on this side would be the force of friction sine theta. Let's go ahead and do an analysis in the X and the Y direction. Let's start things off by looking at the Y directions. So we are going to do a nice little FNet expression. So what's going on in the up and the down? Well, even though we've decreased the speed, so the speed is low, and the car is going to have a tendency to want to drop down the ramp because of this slow speed, there is friction holding it in place. Therefore, it is not accelerating up nor down, so we have an FNet equals 0. I'm going to state that down is negative and up is positive, just for convention. I'm also going to say that the middle of the circle is positive and the outside of the circle is negative. So in the up and the down, in the Y direction, the sum of all forces is equal to 0. And as a positive force, I have a component of the Fn, this Fn cosine theta. So let me put that on. I'll even use red to match the color. Fn cosine, Fn cosine theta, plus, and now in yellow, I have another arrow going up. This would be the force of friction sine theta. So the force of friction sine theta. Now, this is important because we have arbitrarily chosen to have our speed be low, meaning that the force of friction is up. If this speed was high, then the car would have this tendency to go up the ramp. That means the force of friction would be going down the ramp, and therefore the force of friction would be pointing to the negative. And so this positive sign would be different. So I just want you to pause and think about that for a second. This would be a different sign. It would be the negative sign if we had given ourselves a different condition at the start. But since we have gone with the slow speed, we're going to have a plus for the force of friction. And then lastly, of course, Fg is negative. So negative Fg. Now, I'm going to add Fg to both sides. So that gives me the Fg as a positive on the left side of the equation, like this, and it's cancelled out as a negative on the right side of the equation. So this is my statement, okay? If we then do our Fnet analysis for the x direction, or the horizontal direction, we're going to say that we have an Fnet, and since we're in circular motion, we can say that that is equal to the force centripetal, and so we can now make the statement where we start adding the forces that go to the middle. So let's examine our free body diagram. Remember that this direction is to the middle of the circle, and I've called this positive. This would be to the outside of the circle, and that's negative. So let's look at the components of our two forces of interest. So we've got the force normal, which has some x direction to its component, and we have the force of friction, which would have some x direction to its component. Force of gravity has no x component. So I'm going to be adding this Fn sine theta, and then I'm going to be adding the force of friction cosine theta, paying attention to the direction, of course. So let's put in the Fn sine theta, and now I'm paying attention to the fact that the yellow components are going to the left, which I'm calling negative, so I have to subtract. So it's going to be a minus force of friction cosine theta. And again, at this point, I just pause for a moment to think about this positive and negative, recognizing that if I had have chosen for the speed to be greater, then this force of friction would be going down the hill, and therefore I would be adding this force of friction if the speed was greater. But we went with the speed being lower, which means, again, this car is wanting to go down the hill, so the force of friction is acting against that. Now we can just expand these two statements. This is most of my physics done now, and now it's really just a case of algebra and solving for the various bits and pieces that we might want to. Normally in a question like this, you might be asked about the speed or the coefficient of friction or something like that. And once you simplify the equation as best possible, you should see that it pops out relatively easily. Tricky thing here is recognizing how to combine these equations and what to look for as you go through that. So let's do that right now. So we'll start with the y component. So I'm just going to turn this to Fg becomes mg, and then we'll keep the Fn cosine theta plus, now we're going to add in this idea of course, the force of friction being equal to the force normal mu. This is a concept that we can just simply add in. So we can now say that the force of friction here is Fn mu sine theta. And over this side, I'm going to turn my Fc statement into v squared m over r. Of course, I could have equally turned this into 4 pi squared rm over t squared. They are both the same thing. I would just argue that it's more common to have a speed equation in these types of questions. So I'm going with that for now. Of course, we've got Fn sine theta, and then I'm going to do the same thing here. I'm going to turn the force of friction into Fn mu cosine theta. So now we're looking for something to substitute in from one side of the equation to the other. And of course you can have a bit of fun and play around with this as much as you like, but I'll go ahead and give you the spoiler. It's going to be mass. So I'm going to rearrange the y equation to solve just for mass. So that is, of course, Fn cosine theta plus Fn mu sine theta all over g. And then this whole thing can just be slotted in to here. So I'm going to go ahead and expand that out. So there we go, we just added in, well, we substituted in this equation for m, and we have this big long expression here. Now, one thing you can do at this point, and well, actually you need to do, is recognize that every part of this equation is being multiplied by Fn. So if we divide everything in this equation by Fn, which we can do, we cancel it all out. So all of the Fn's disappear, and so we're left with an equation, so v squared over r, actually I forgot the g, over rg cosine theta plus mu sine theta is equal to sine theta minus mu cosine theta. And I'm just going to leave it at that. You can play around with this however you like. You can solve for various different bits in it. One thing I would remind you about is just thinking about this plus minus in both sides here. Of course, remember that this derivation here came from the speed being slow, and with that meaning that the car or the object would have a tendency to go down the ramp. If you had it going fast, and therefore the car or the object had a tendency to go up the ramp, these signs would be reversed. In other words, the positive would be a negative, the negative would be a positive. So it's just worth thinking about. Otherwise, at this point, yeah, you could solve for whatever you wanted to. Most of the physics was done by doing the free body diagram and the F-net expressions, and this last bit is really just algebra, and you can use whatever values you need to solve a problem.